Okay. So today we're going to go over basic summary statistics. So these are ways that we can describe data that we've collected. So our goal is to describe and make inferences about a population of interest. So usually we can't ask questions to the entire population. We have to take a sample and find out information from them and then relate it back to the population in general. And it's important that the sample we choose is representative of the entire population. So for instance, if we wanted to know the average height of a student at UNC, we wouldn't go select the basketball team as our sample. We want to make sure that the sample includes people from all different backgrounds of height or whatever we're looking at, so it's representative. So a parameter is a value that describes the population. So for instance, it's the average number of children in a household. It's a fixed value and it's unknown. The reason it's unknown is because we can't ask everybody about how many children they have or things like that. We want to create an estimate of that value by taking samples. So we take statistics, which are estimates of the parameter based on a sample, and we want to relate that back to the entire population. So these statistics may vary from sample to sample. So if we selected 10 students and asked their height, that would be different than if we asked another 10 students. But roughly, we want to use the statistics we gain from sampling and relate that back. So if we randomly survey 300 US households and find that they have 2.1 children on average, then 2.1 is a statistic. So our goal with statistics is being able to take that value that we got of 2.1 and see how close it is to the parameter that we want to figure out. So here's a graphic to illustrate the difference between a parameter and a statistic. So a statistic is the value we get from the sample, and then we want to make inferences about the parameter, which is the value for the entire population. So the data that we can collect through sampling is either categorical or quantitative. Categorical are observations that are classified into several groups or categories. These are more like the word questions you ask, like gender or ethnicity or country of residence. It can also be a scale, like what's your pain level, low, medium, high, things like that. And then there's quantitative data, which is a numeric variable, such as blood pressure, age, salary. And the quantitative data is what we'll be focusing on today. So to get more detail about the different types of categorical data you can have, there's dichotomous, which are two possible outcomes, such as yes, no, pass, fail, things like that. Then you have ordinal, which has inherent ordering. That's one way to think about it. Is, for example, pain relief, none, small, moderate, complete. So you can order those, but they're still not quantitative. Then you can have nominal categorical data, which has more than two outcomes, and it isn't ordered. For example, ethnicity, country of origin, because you wouldn't want to order those. There's no value associated with them. So we're going to go into an example here of quantitative data using urea in liver cells. So a researcher measured the urea excreted in her liver cell samples. That's hard to say. And we got this data from Valerie Soldato. So we're going to be using this data set throughout the lecture for our examples. So here you can see the column title is urea, and then we have all of these values here. So we want to be able to take all of these numbers and summarize it in a way that we could explain what we found to other people interested in our data. So thankfully we can use R to do all of the statistics for us. So first here, this is an example of how we get R to load the data, so then we can perform statistics on it. So first we name the data set urea_data. We read in the CSV file and we attach the file that we just created, and here is the data that we had imported. So what the attach command does is it allows us to reference the columns of the urea_data frame without using a $. So that means that we can just reference the column as urea and it will spit out all of the data. Does that make sense? Instead of using the $. Okay. So first, if we were to use the $to reference the column, it would give us all of the data. And then when we attach it, we can just reference the column urea and it spits all of that data out. So it's a way to simplify the work that you have to do in R. So the first statistic that we're going to talk about today is the sample mean. It's better known as the average, and I'm sure all of you have seen this before. So it's the sum of all of the values that we collect divided by the number of samples. So for instance, okay, I guess that's in a few slides. So the sample versus population mean, the one we saw on the previous slide is the sample mean, since it's based off of a sample. So if we collected the height from 10 people, we'd add up all of those heights and divide by 10. So we want to use the sample mean to relate it back to the population mean. But we hope that the sample mean is a good approximation of the population mean. And in the future, we're not always specify if we are considering a sample mean, but usually for the most part it will be a sample mean instead of the population mean. So instead of having to do this all by hand, we can have R do it. You can see that we did it all by hand here in R, and we got the value of 35.13. We can use the command mean and then the column that we want to take the mean of, and it will spit out that exact same value. So it saves you some time. The next statistic we're going to talk about is the median. You can see this little Dilbert comic there. So it's kind of funny. I'll go on to describe what the median is. So it's the middle number of the data. So here, if we were to list out all of the values we had collected in our research, we'd find the one that's in the middle and select that, and that would be our median. If there's an odd number of observations, then the median is simply the middle value. If there's an even number, then you take the average of the middle two values. So one way to do this is to use the sort command in R. So what that does is it arranges the data from smallest to largest, and then you can go through and find it. You can also reverse the order of sort, so it will go from largest to smallest. And here you can see that command, you have the column that you want to work with, and then decreasing equals true if you want to go from largest to smallest. You don't have to specify that if you want to go from smallest to largest. But you can just enter the median command and it will do all of that for you. So one reason we would want to use the median is it's not influenced by extreme values, and we call that being robust. is the definition if it's not influenced by extreme values. The mean is, if you have a very extreme value, it will pull the mean of the data to the right or to the left, whereas the median is just the middle value. It's always this right in the middle. So I'll show you an example here of what that means. So if we had, for instance, we had a test, and these were test scores. The first data set, somebody slept through the test, so they got a 0. But if they would have shown up to take the test, they would have gotten a 77, we'll say, for instance. So if you were to look at the first data set, the median is 80, because that's the value right in the middle, but the mean is a 67. Whereas if you had replaced the 0 with a 77, you get a mean of 82. So the first data set makes it sound like the test is really hard if you say the mean's a 67, whereas the second one, it's the mean better reflects what's actually going on. So in this case, you'd want to use the median as a way to describe the data because it's robust. So the data is symmetric if the mean and the median are nearly identical. So on the previous slide with the test data sets that we were looking at, for the second one where we had that 77 instead of a 0, the mean and median would be about the same, so it would be a symmetric data set. If the mean and median aren't roughly the same, then we have skewed data. So you can see here that it's not that perfect bell curve. It's got a tail that goes off to the right because the mean is higher than the median. Okay, so it looks like my little voice recorder thing is taking up the part of the screen. If a data set has a heavy right tail, so that means if it kind of goes off to the right, that means it's right skewed, and the mean is greater than the median. If the data set is the other way, so it has a heavy left tail, so that means that there's some extreme values, extreme small values, it's said to be left skewed, and that's when the mean is less than the median. So I put some examples here of right skewed data and a little left skewed example where the median is greater than the mean. So this right skewed, for an example, would be income. So most people have a medium income, but you have a few people who make a lot more money who throw the data off, skew it, so that it would be right skewed. Another way that we can describe our data is with quantiles. So we look at the percent of data, for example, the X% quantile of a data set is the point at which X% of the data is smaller. So we wanted to look at the 25th percent quantile. That would be the point at which 25% of the data is smaller than that. So it's a way to like split up the data into little sections so we can look at it that way. And just a note here, different programs compute quantiles differently. So if you run it in Excel, I think Excel has a command, and you run it in R, they might give you different values, but it's still, you can use either of them. The 25th percent and the 75% quantiles are known as the first quartile and the third quartile because it splits up the data into that way. Okay. So you can have R generate quantiles for you. In this example, you specify the quantile you want to find. So the first one, this example, quantile urea 0.25, that gives you the 25th percent quantile, and then you can do the 0.75 as well. So this if you want to be like very specific at what percentile you're looking at, you'd use this quantile command. So you could do anything 0.45, 0.33, whatever you want to look at. You can see if we go back to the data set that it gives us values that are in between those highlighted numbers. So it splits up the data that way. Okay. The 5 numbers, minimum, first quartile, median, third quartile, and maximum, are often used to summarize the data. And we can determine if the distribution is skewed and if there are extreme values. So what this means is if you had a data set and you looked at the quantiles, and for instance, the distance between the 25th and the 50% quantile is a lot smaller than the distance between the 50 and 75, it means that you have a lot more data at the beginning and then kind of tapers off, so you have skewed data set. So if the distance is the same between all of those quartiles, it means that it's one way to look and see that it's not skewed. So just a quick little review. You remember what the 50% quantile would be? Yeah, that's right. Okay. So in R, there's multiple ways to find quantiles. You can use the quantile command. Here we use quantile urea, which is the column name, and it spits out the minimum, which is the 0%, the 25th, the median, 75th, and the maximum. You can see that this is the same function we used on the previous slide, but here we don't specify which quantile we want, so it just spits out all those 5 values. Another command we can use is the summary command, and that's a little different than the one you saw before in that it gives you the mean. But besides that, it's basically the same. So if you have to compute the mean anyway, the summary is a good way to go because it just does all of that for you in one command. The interquartile range is another statistic we can look at, and that's the third quartile minus the first quartile, so it contains 50% of the data. So it measures the spread about the median, and it's robust to extreme values. So if you want, if you have a lot of extreme values and you want to be able to look at where the majority of the data lies for that data set, using the median and quartiles and interquartile range is one way to do that. For example, in the data set that we're looking at throughout this lecture, the interquartile range is 38.98 minus 31.645. So 50% of the data lie within 7.335. Okay. So if we want to look at some way to describe the distance from the mean, we'll use the standard deviation. Should I go back to that slide? Are you still looking at it? Okay. So I'm going to write this up on the board if there's chalk, or I guess, yeah. Because we're going to talk about it in the next few slides, so this way you can see it while I talk about it. So hopefully that's probably right behind my head, isn't it? Okay. So you see here that it's kind of a complicated formula because you're taking the square root of 1 over n minus 1 and then taking the sum of the difference squared between each observation and the average value. So it's sort of complicated, and thankfully we can have R or other programs do it for us. So it's mainly used because it has nice mathematical properties that we'll discuss later. So we're going to go through why we use this. So first, when we take the squared difference, it makes it positive. So we want to look at the difference from the mean. We wanted a positive value. So we can say that the standard deviation is, for instance, like 0.5. So that means that 0.5, you have the mean, and then you have plus 0.5 minus 0.5. The majority of the data lies within that area. You could use absolute value to specify that you want a positive value, but when you're using math to just go through this, it makes it really complicated having absolute value signs. So it's no longer differentiable, and I won't go into that because it's really long and complicated. So squaring the difference produces a nice mathematical properties. That's basically this summary there. So why we divide by n minus 1 instead of n is that if you just use n, the estimate is biased. It's too small. So it will give us a standard deviation that is smaller than what the actual value would be. And so since we want to overestimate the variance and the standard deviation, we use n minus 1. So variance is the standard deviation squared, if that wasn't clear. For large data sets, it really doesn't matter because you have huge value for n, so it doesn't matter if it's n or n minus 1, but this is the definition that we'll stick to for standard deviation. So in R, you can just use the command SD and it will do it for you. So instead of having to deal with this equation, which takes a long time to work with by hand, R does it in less than a second. So standard deviation measures the dispersion about the mean. It's like the interquartile range, but in this case, it's dispersion around the mean. Interquartile range is dispersion around the median. The standard deviation is always non-negative. It has the same units as the mean, and it's not robust against extreme values. So if you have, like the test example, if you have a 0, it'll make the standard deviation a lot greater for that data set than the one where you had a 77. So the median or interquartile range may be preferable when the data is skewed or extreme values exist, but usually mean and standard deviation are used. So that's what you'll be dealing with mostly in the next few lectures, probably homework too. So I guess we'll go back, and is there anything not clear? Did I go through anything too fast that I'd like to go over again before we kind of sum up what we learned? No. Because this is all, have you all seen standard deviation, mean, median? Okay. So we review what we've gone over today. We estimate unknown parameters by using statistics. So the statistics help us to be able to understand parameters from a larger population. So we take the mean of a sample, and that will give us some understanding of the mean of the entire population. And in future classes, you'll learn how you can make estimates, be 95% confident that your mean is within certain values for the entire population. But right now we're just learning what these statistics are. So we can have categorical or quantitative data. Categorical data is classified into several groups. So it's more the race, gender, things that you can describe with words, and quantitative data is numeric, and the quantitative data is what we can perform statistics on. Mean and median are two statistics used to estimate the center of a data set. The mean is not robust. It can be skewed if there's extreme values. The median is robust. It's always just the center of the data. If you have the mean and median similar, then it's not skewed. If one is greater, if the mean is greater than the median, you have a right skewed data set. If the mean is less than the median, you have a left skewed data set. The interquartile range and standard deviation are used to measure the dispersion of a data set. The interquartile range is used for the median, and the standard deviation is used for the mean. So the median and interquartile range are resistant to extreme values, and the mean and standard deviation are not, like we just discussed. And then we'll go through these R commands. Have you used R before? No? First time?
I introduced it on Wednesday, so not really.
Okay. So it probably seems a little daunting, like trying to work with it. But once you just remember a few basic commands or just how to find things online, it's really easy to work with. So this is just a little, I guess, cheat sheet that you can use for finding basic summary statistics. So the attach command allows us to reference the columns without referencing the data frame each time. So that was that weird, when you saw that weird like $sign and then the column, you don't have to do that when you use attach. You can just reference the column title, and then it gives you all the data. The sort command sorts the data from smallest to largest. The mean returns the mean of the data. Median gives median, and these just make your life a lot easier instead of having to do them by hand or in a calculator. These are just easy ways to do it. The quantile returns a specific quantile of the data. If you specify, you put up like a comma and then 0.75 or whatever value you want to look at. If you don't specify the value, it will give you the minimum, the 25th, the 50, 75, and maximum. The SD function returns the standard deviation of the data, and the summary gives the quantile variables and the mean. So that's a really good function to remember when you want to look at the data. So all of these commands and all of the summary statistics we've learned, they're ways that you can describe the data without having to go through every single number and looking at it that way. It's just ways that you can communicate your findings to other people, ways for you to understand how the data could be skewed. So it's important to be able to know what these statistics are when you're running through data. So I don't know if you guys saw in the email the discussion section next week on Friday from 3:30 to 4:30. I'll be going through an example with R, and if you have questions that you want to ask, we can go through them then. But R's fun, makes life easier.
We'll hopefully have a room for a discussion section soon. I sent in an email to reserve one, and they haven't gotten back to me, but hopefully soon.
Mm-hmm. And I tried to send an email to the class about my office hours next week. I don't know if it went through, because I was trying to do it on Sakai, but okay. So they'll be at 4:45 to 5:45 on Monday if you have trouble with your homework or if you just want to talk about statistics. So any questions? Anything you want to go over again? No?